welcome to Oddly Real. I'm Nem Stefanovic. Computers are now everywhere, sitting on our desks at home and work, but also embedded within our personal devices like phones, watches, and even home pregnancy tests. Most modern electronic devices have some kind of computer or microcontroller within them. We are so used to working with digital devices, we essentially take them for granted. Yet, if you take a second to think about it, these are actually very extraordinary machines. A computer is capable of performing tasks that would normally be accomplished by intelligent beings with minds, like ourselves. In many cases, computers actually perform extraordinary calculations or run complex simulations that are beyond the abilities of human beings. How can a device which doesn't have a mind of its own carry out this intensive mental work? In other words, how does a computer work? Computers do not think for themselves, they only follow instructions. At their most basic level, transistors and logic gates can physically capture logical processes. They have inputs, perform a task, and have output. In fact, these components can be combined into more intricate arrangements to perform addition, multiplication, and many other computer operations. In this episode, we will explore transistors and logic gates and show some examples of exactly how they can be used to perform calculations. Let's start with the abstract concept of a logic gate. A logic gate is a small component that has some inputs and some outputs, which are electrical signals in the form of voltages. In this case, there are only two kinds: a low voltage, like 0 volts, which represent a value of 0, or high voltage, let's say 5 volts, which represent a value of 1. Since there are only two possible values, 0 or 1, we call this a binary representation. Each digit, which can take on a value of 0 or 1, is called a binary digit, or bit for short. Notice that this is different from our usual decimal number system, which takes on 10 different values for each digit, from 0 to 9. Let's start by looking at an example of an AND logic gate. It has two inputs, one bit on each input, and it has one output, another bit. The behavior of the AND logic gate is fully described using a truth table. We can map every possible set of inputs to its corresponding output. Since there are only two inputs, and each input can take two different values, that means there is a grand total of 4 possible input combinations to the gate. Notice the AND gate mostly results in a 0-bit output for any combination of inputs, except when both inputs are 1. In this case, the output becomes 1. There are other common logic gates, each defined with a unique truth table. The OR gate has an output of 0 only when both inputs are 0. If at least one input is 1, the output becomes 1. The NOT gate has only one input and one output. It simply inverts the input value. If it is 0, the output is 1. If the input is 1, the output is 0. Another useful logic gate is the exclusive OR gate, or XOR. In this case, the output is 0 when both inputs are 1 or both inputs are 0. The output is 1 only when the inputs are different values, one with a value of 1, the other with 0. Logic gates like the NOT, AND, and OR gates are the building blocks for calculating machines. But how can we make them physically real? How do we actually build a logic gate? At their core, there is an even simpler physical component that we can use to actually create a logic gate. This component is called a transistor. A transistor is essentially an electronic switch, at least how we will use it here. Specifically, we can build our logic gates using NMOS transistors. The transistor has one input which controls if the switch is closed or open, making a circuit connection or breaking the connection respectively across its ends. The NMOS transistor is turned off, or an open switch, when 0 volts is applied to its input. The transistor is turned on or becomes a closed connection when there is a high voltage, like 5 volts, applied. Let's create a simple circuit to create a NOT gate. We connect our circuit to a 5-volt power supply, which passes through a resistor R to prevent too much current from going through the circuit, and a transistor, our switch. The other end of the transistor is connected to ground to complete the circuit to allow for current to flow when the switch is closed. If the input to the transistor is 0 or 0 volts, the switch is open, meaning there is no current flowing from our 5-volt power supply to ground. In this case, the output is 5 volts. In other words, a 0 input produced a 1 output. Conversely, when the input is 1 or 5 volts, the switch is closed. This creates a connection to ground, which pulls the output voltage to the ground voltage, which is 0. Thus, an input of 1 makes an output of 0. This is exactly the desired behavior of a NOT gate. How can we create an AND gate using NMOS transistors? An AND gate has 2 inputs, so we use 2 transistors. Our circuit is connected to a 5-volt power supply through a resistor and passing through 2 transistors in series to ground. In this case, the output is going to be 5 volts if either transistor is open, since there won't be a connection to ground. The only time the output voltage is 0 is if both transistors are closed at the same time, or both have inputs of 1. But wait, that's not quite right. According to the AND gate truth table, we should get a value of 1 when both inputs are 1, not 0. It's the opposite of what we want. And this is true. We actually created a negation of an AND gate here called a NAND gate. This is easily fixed. We can cascade the output of the NAND gate with the NOT gate that we created to invert the output value, and the output will be exactly what we want for an AND gate. Finally, we can also build an OR gate using NMOS transistors. In this case, instead of having 2 transistors in series, like in the AND gate, we put the transistors in parallel. Now, whenever any one of the transistors has an input of 1, the output will go to 0. Again, this results in the negation of the OR gate output, something called a NOR gate. We cascade the NOR gate output with a NOT gate, and we get the desired OR gate. Note that in modern-day computer processors, transistors and their associated logic gates and digital circuits are all etched together on extremely small scales on silicon semiconductors. This is a highly specialized fabrication process. For example, very large-scale integrated circuits, or VLSI, can create tens of billions of transistors on a single processor chip. Apple's M3 Max processor contains 92 billion transistors. Computers use a slightly different number system to our own. Human beings use a standardized number system called the decimal system. It's called a base 10 number system since there are 10 different values, 0 through 9, for each digit. So starting from 0 and counting up, we go through those 9 digits until we reach the number 10. In this case, we've run out of digit values, so we add 1 to the next digit and begin counting from 0 again from the first digit. We can represent any integer value this way. Each subsequent digit that we use in our numerical representation is a placeholder for a power of 10. So for example, take the number 2083. We can rewrite this number to show its digits and their powers of 10 placeholders as follows. 2 times 10 to the power of 3 plus 0 times 10 to the power of 2 plus 8 times 10 to the power of 1 plus 3 times 10 to the power of 0. In computers, we use a different number system called binary. It's a base 2 number system, meaning there are only 2 values for each digit. So starting from 0 and counting up, we count up to 1, and then we've already run out of values. In order to get the number 2, we have to add 1 to the next digit and start counting from 0 again from the first digit. Here's the binary representation for the first few numbers. Each subsequent digit that we use in our numerical representation is a placeholder for a power of 2. So for example, take the number 14, which is 1110 in binary. We can write this number to show its digits and the powers of 2 placeholders as follows. 1 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 0 times 2 to the power of 0. Let's build an adder for 2 binary digits, or bits. We'll start with the truth table. Since there are 2 inputs, one for each bit, and each bit can only take on 2 values, that gives us a total of 4 possible combinations of input values. If both inputs are 0, their sum, 0 plus 0, is 0 in the output. Also, if one input is 1 and the other input is 0, then we get the sum 0 plus 1 equal to 1 in the output. But we have a problem if both inputs are 1, since 1 plus 1 is 2, which is too large to store in one bit. Recall, the binary representation for the number 2 is 1, 0. In this case, we actually need to include one extra output called carry out to our bit adder to capture that extra digit. The first digit would be 0 in this case, and the carry out would have the value of 1. How do we build this device using logic gates? We look at the truth table. Notice that the sum output column compared to the inputs is exactly an XOR gate. Next, if we compare the carry out column to the inputs, it is just an AND gate. Thus, 2 logic gates, each connected to the inputs, can be used to create our adder. This simple bit adder with carry out is called a half adder. Why is it called a half adder? Even though we've accounted for an overflow from our sum using a carry out output, notice that we haven't included a way to carry in an overflow from another adder into this one. This is a necessary capability for more complex calculation circuitry. We won't go into the full analysis here, but here's what a full adder circuit looks like and its associated truth table. Instead of 2 inputs, the carry in is used as a third input, and its value is summed up with the other inputs. For example, the last row in the truth table shows the inputs as 1, 1, and 1. When summed, they equal 3. Notice that the output value is 1 and the carry out is 1, which gives us the number 1, 1 in binary, which is the representation of 3 in decimal. Adding bits together seems fairly straightforward. How can a computer add larger numbers together? Well, let's look at an example to add 2 larger numbers together using something called a ripple carry adder. Here, we make a series of additions between 2 bits where each pair of bits represents the pair of digits at each subsequent binary position. We start from the right-hand side where we add the 2 digits to get an output and a carry value. The carry out value gets passed to the carry in bit in the next full adder. Much like when we add 2 numbers on a piece of paper, we sometimes have to carry forward to the next digit if the number is too big. This same procedure is then repeated again at the next full adder and continues. Hence the name ripple carry adder, as the carry out bits ripple through the adders until we ultimately get to the final answer. This particular adder is actually not very efficient, since each stage has a processing delay that has to wait for the prior stage to complete, making it relatively slow. There are other implementations, like the fast adder. However, there also tends to be a trade-off in complexity and cost of these circuits for the added performance benefit. What about multiplication in computers? How does that work? Well, recall from our early days in elementary school, we were taught a long form style of multiplication, where we'd start from the least significant digits on the right-hand side of the bottom number, and we started multiplying through the digits on the top. When doing this, we get a new number which we write below. Next, we'd move one digit to the left on the lower number and repeat the process, also shifting the result by one digit and writing that below the prior result. Ultimately, we'd be left with a few rows of results, all shifted one digit in place from the prior, which we'd have to add up to get a result. We can implement this kind of multiplication process directly in computers using logic gates. However, in this case, we would use binary as the multiplying numbers instead of decimal. In fact, we can also reuse our full adder circuit with some extra modifications to architect an implementation for multiplication. Logic gates are not just used for addition, multiplication, or other numerical calculations in computers. They form the basis for many other kinds of operations and capabilities. For example, a gated D latch is a kind of memory storage device, which can be assigned a value to store when the computer clock signal is high. When the clock signal drops to low, it retains that stored bit value. This is also a component in a D flip-flop, which stores and retains a bit of data via a change in the clock signal. Digital logic circuits can also be used to build counters that continuously increment their values, multiplexers which select a signal to pass through from a set of different signals, and entire step-by-step sequences of action through the use of finite state machines. There are even microchips called field programmable gate arrays, or FPGAs, that let users program their internal hardware to create their own arrangement of digital circuitry. The FPGA digital logic can then be reprogrammed and reconfigured any number of times to build new circuits. I hope this episode provided some insights into the internal workings of computers and calculators, and I hope you enjoyed it. Remember, oddly real, really interesting.